Okay, I can start. We'll start on page 13, unless you have any specific questions. Okay. Okay, so number one on page 13, function has continuous derivative. Table gives a value of f and its derivative for x equals 1 and x equals 6. The integral from 1 to 6 is 9. What is the value of 1 to 6 of 3x f prime of x dx? So we are going to try to go through integration by parts here. We want to basically, if we go through substitution, it's not going to quite get everything to work out the way where we can find a rule. So integration by parts, we can let the 3x be the f. We can let the f prime be the g prime. We go through integration by parts or IB pad method. I think that is preferable, especially if it's manageable. So we start off with 3x and f prime on this side. We know that on the left column, we're going to be finding derivatives. So 3x becomes 3, 3 goes to 0. On this side, we're going to take the antiderivative. So f prime becomes f, and then the antiderivative of f, which is be the integral of f, since we don't have something that can turn that f into, so we'll just call it integral. Okay. Assign a plus minus, and then multiply by the diagonal. So we have 3x f of x minus 3 integral f of x. Right. We know that ultimately we're evaluating this between 1 and 6. So I can break this up into two separate parts here. I can say, hey, I can evaluate that 3x f of x between 1 and 6. And then I can also evaluate that 3 integral of f of x from 1 to 6, which is essentially this here. And if we write it this way, maybe it's a little bit easier to match that what it's equal to. So we know that this piece can be used to resolve that portion. But let's do this one. So upper bound first. So 3 times 6 times f of 6 minus, then plug in the 1. 3 times 1 times f of 1. And then minus 3 times 5. So now we can just rely on our table here. F of 6 is 8. F of 1 is 2. And then minus 27.
How can you choose to plug in f of 6 and f of 1? Like, where did the 6 and 1 values?
They're coming from the fact that ultimately it's a definite integral. After we resolve this 3x f prime integral, we have to involve the 1 to 6. Okay, 1 second. Depends. Sometimes I have like, concept like that. Yeah. Oh, you're in the back there. Hopefully I did like actually just see what my phone's acting up. This week, I know. Unfortunately, find pin date. Say, what's your table? For grade 6, we do 8 inches. Just like, there's a phrase, I'll do it tomorrow. Thanks so much. And why? Yes.
There like a restriction on when you can use tab method and all?
Yeah, if you see natural log, then you can't do tab method. Okay. So if it's like natural log and 3x, then you have to go through your original integration by parts rule. So number 1 on quiz review 1, here you see natural log, so we have to go through this original integration by parts rule. And then your natural log will be your f, and the other expression will be your g prime.
And that's only if there's natural log.
Only if there's natural log. Okay. Yeah, so typically, unless there's natural log, I think we just prefer to just always do tab method. But for natural log, kind of force them to the original rule.
And then what does the I stand for in that acronym?
Oh, inverse trig, which we're not going to see much.
Oh,
It's going to be no.
so then for the last problem, how come you chose to plug in 6 for one of the x's and then 1 for the other x? So at that bottom equation there.
Oh, this one here?
Yeah.
Okay. So once we're here, we know we have to plug in the 6 and the 1. I'm just breaking this up into 2 separate regions here. So I'm doing the 3x f of x from 1 to 6.
Mm-hmm.
And I'm also doing the integral here from 1 to 6. But I'm putting it back in this form so I can kind of match the fact that, okay, this is already resolved. I know that's already 9, so I can just leave that alone. But this one is upper bound minus lower bound.
Oh, okay, so you're still solving that integral.
Right.
Okay. And then when you're multiplying by f of x, how do you choose what value you're plugging in for x? So you're done with everything else.
Mm-hmm.
You multiply by f of x. How do you choose?
This one here, or?
When you're doing the tab method, you multiply 3x times f of x.
Mm-hmm.
How do you choose the x for f of x?
Well, initially when I do tab method, I don't know what x is, so I left it in terms of x. But then I know that ultimately in the end, I'm trying to find the definite interval from 1 to 6. So I know that my bounds are 1 and 6.
Okay. Oh, okay. I see what you did.
Okay, number 2, also integration by parts, because we have 4x e to 3x plus 2. I mean, normally we would try to go through use substitution, but we know use substitution is not going to quite work, right? That exponent power is not going to quite cancel that 4x. So our next option is, okay, we see 2 different types of functions. You have your algebraic, you have your exponential. So we can go into looking at tab method as our
So if you had an exponent, like what it is now, then is there like a preference to what is f and like what's g?
Oh, we mean at this stage?
Yeah.
So if we do that LIATE formula, then algebraic is going to take priority over exponential. Right, so whatever comes earlier in the acronym is going to be your F.
Okay,
and whatever comes after is going to be your G prime.
okay. Is the L for logs?
No, yeah, L is for logs.
Then how would that, because aren't we not supposed to use logs for, or,
Well, this one is algebraic and exponential.
okay. And then, like, is the acronym used for something else, like the logs?
Well, if there's logs in the problem, then I would use log. I would choose the logs
Oh,
as the
so
F.
like the other way.
Right,
Okay.
right. But because algebraic can be the F, I don't have to go through my original rule. I can go through tab. Okay, you can sit. You have your phone?
It's.
Okay, got it. Thank you. You can use your calculator.
Oh.
So from e to 3x plus 2, I have to find the antiderivative. I got to go through use substitution just to. You can use this one.
Okay.
Yeah, alpha second y equals gets you that. And then
Okay.
do-
Okay.
So there's a 1/3 that's going to always come out of this use substitution.
Just technically take the derivative of the top, or wait, is there a shortcut, or would you always have to go through use something?
I mean, there's a shortcut if it's a linear. You just find the derivative and then just make sure you flip it.
Okay.
Yeah. It's the opposite of chain rule, right? So instead of times 3, it's times 1/3.
Oh,
But if you don't want to memorize that rule, you can always go through use substitution, convince yourself that it's going to be the 1/3 that's going to come out of it.
okay.
So if we go through use substitution again, we know after one time, okay, it's going to be another 1/3. So times 1/3 is 1/9. So now we can go through our pairings, positive, negative, positive. So we get 4/3 x e to 3x plus 2 minus 4/9 e to 3x plus 2, and then plus c.
Hey, could we just leave it like that? Or? Okay.
Okay, any questions with 2? All right, number three, we see all these factors in a denominator. This is going to be a good candidate for partial fraction. So ideally, we would like to split this up into three separate fractions. First fraction being x minus 1, second fraction being x plus 2, third fraction with x minus 4. I'll just take it. You can put your things to the front. I have you in the back. You can use the calculator as well. Okay, so we can find factors from the denominator. Okay, so I'll go through the cover-up method here. If I want to resolve well, if I want to solve for a, I want to cover up my x minus 1. So go ahead and cover up your x minus 1 and replace all the remaining x's and include the numerator as well in finding your a value. So 1 in for x, I get 1 plus 2, which is 3. 1 minus 4, which is negative 3. So 3 times negative 3 is negative 9. And then we have the 2 in the numerator, so 2 over negative 9. So my a is negative 2. That's okay. To solve for b, I'm going to cover up the x plus 2 and then replace all the x's with negative 2. So negative 2 minus 1 is negative 3. Negative 2 minus 4 is negative 6. 3 and 6 is 18. 2 over 18 is 1 over 9. Okay, let's plug 4. Cover up the x minus 4, plug 4 into the remaining. 4 minus 1 is 3. 4 plus 2 is 6. 3 and 6 is 18. 2 over 18 is also 1 over 9. Okay, so essentially, we can put all these fractions where a and b and c are. So I'm going to, but we haven't resolved the integral yet, but we've made the integral now, hopefully an easier problem to do. And then if you want, you can just pull all those fractions out as coefficients if it makes it easier to look at. But ultimately, these are just pretty easy natural log problems. None of them require use substitution since these are nice linears without any derivative other than 1.
If we get all of our values like A, B, and C, is it okay if we skip the integral step and just?
Yeah, if you want to go from here to here, you can.
Okay.
Yeah, you go directly to here. Okay. All right, number 4, we see improper integral there. We'll let B represent that upper bound. Now we just go through how we normally would, even if that bound was a real number. So now we can kind of convince ourselves what's happening with each of the fractions with that moving B value. So if we imagine B getting larger and larger, that's causing this denominator to get larger, but it's causing the overall fraction to be 0. So that's a good sign. We know that this is probably going to converge, and we know that's going to 0 out. That's a real number. And then we're just left with that 1/8. And so there's no infinity that's causing this to grow without bound. So we have a distinct solution to give for number 4.
What situation would it?
If, let's say, the B was in the numerator, if it was like B squared over 2, then if I plug infinity over B, if I'm convincing myself that one of the fractions is heading to infinity, then it's going to wipe the whole thing to infinity.
Okay.
And that's considered your diverging.
What if it just goes to 0?
Then it should be 0.
Okay.
Yeah.
So it would only diverge if there was an infinity.
Right. So you're either getting infinity or you're getting a real number. Okay, I'm not going to put arc trig on the quiz, but I think it's, we can still go through the process here. So number 5, this fits into an arc sine rule here. My A is 3 and my U is X. Once we see that rule, we can apply it and realize it's basically just going to be arc sine of X over 3. And we know there's an issue at 3 because 3 is causing the denominator to be 0. So there's a discontinuity, or in this case, vertical asymptote. So we have to approach 3 from the left because our graph is between 0 and 3. So if our graph is between 0 and 3, then the graph is going to have to approach 3 from the left side of 3 because we're not talking about the graph on the right side of 3. We're talking about the graph on the left side of 3. So it's approaching 3 from the left. And then once we resolve that as arc sine of X over 3, we can plug in our upper and lower bound. And then 3 from the left side of 3. We always want to try to evaluate with the real number first. And then if something is not quite resolved, then we can use decimals. But we always want to try that integer value first. So if I plug 3 in, let's see if that works. Arc sine of 1, that's asking when is sine of theta equal to 1? Sine of theta is equal to 1 at pi over 2. And then we know arc sine is 0. When is sine equal to 0, which is at 0? So that's why we end up with pi over 2.
What would we do if the discontinuity was in between the bounds? Or are we always going to see it?
Yeah, so if it's in between the bounds, you got to split up into 2 separate problems.
And then you do 0 to A and
0 to A, and then from B to 2 or whatever.
Okay, so you do B to.
Right. So let's say I had there's discontinuity at 1, right? So we got to break this up into from 0 to A. And from A to 3. And this will be approaching 1 from the okay, sorry. So 0 to A, we're on the left side of A. So approaching 1 from the left.
So you have two different ones.
You have to do, yeah. And this one is on the right side of A. And then you resolve the integral and then plug in upper bound, lower bound, and then plug in 1 to see if any of them gives you infinity or 0.
I think they should.
Mhm.
And then would it matter if you did like 0 to B, B to 3, or the?
That's fine, yeah.
Doesn't matter.
The letter doesn't matter.
Okay, they just have to be the same.
Uh,
That doesn't matter.
doesn't matter either.
Okay.
Yeah, you can use different letters as well. But you have to treat them as independent things. Yeah, and if one of them diverges, then the whole thing is going to break down.
Okay.
They just have to both be real numbers if we want it to be a converging solution. But if one of them is not real, the whole thing breaks down.
So to solve this, like use natural log or.
Mhm. Yeah.
So you'd use the natural log of y equals that equation you just said.
Let's see, natural log. Um, let's see what we get. So if we try to plug in A, it'll be 1, right? Natural log of 0 is not defined. But if I choose like 0.1, 0.0001, sorry, if I choose 0.9, 0.99, 0.999, this will get smaller and smaller, and this is going to go out to infinity, and that's going to break down.
Okay.
So
And then are
this
you
will
using the
diverge.
limit notation at all, or is that just there to show that you're doing it from the left?
It can be both.
Mhm.
If the limit notation is there because, well, first off, we need it. And second, it kind of helps you decide, if something gets stuck, it gives you some additional information to plug in.
Okay.
Remember, we always want to plug in the real number, right? If a real number works, then great. If it doesn't work or there's an issue, then start playing with decimals and convince yourself, okay, is that headed towards 0 or is that headed towards infinity or is it headed towards a real number? Okay, Euler's method. So my A is 1, my B is 3, and my N is 2 steps. It's basically y equals mx plus b here. Okay, so we know we're going to start at 1. We're going to keep incrementing by 1/2 until we reach, I'm sorry, 2/2. It's step size of 1 here. 1 plus my delta x of 1, and then that should be in 2 steps I can get to my destination. So if I plug 1 into the function to get my y value, h of 1 is going to be 0. Right? 1 to 1, my balance is not changing here. So h prime would be the derivative of this, which would just be 1 over x squared, right? For second theorem allows that to go away. So if I plug 1 in for x, 1 over 1 is just 1. So y equals y sub 0 plus my slope times delta x, which is 1.
So to find y, like the very first y, you plugged in 1 for in the bounds, which because that's just like 1 to 1 and 0. But then why would you plug in the x back in st later when you remove the bounds because you're like doing x like h prime of x?
Why would I remove the bounds here?
Well, I get why when you do h prime, you remove the bounds because it's like,
Second theorem.
yeah, but then like, why would you put it in as t? It's because like you're replacing, or does it matter?
So here's second theorem. It says that if I want to find the derivative of depth integral, I'm going to plug the upper bound into the function. And then multiply by the upper bounds derivative. So then if I apply that process here, I'm going to plug the upper bound into my expression and then multiply it by the upper bounds derivative. So nothing's going to happen because it's going to be just times 1.
Oh, okay, that makes more sense.
Yeah, we're just following this. I'm just skipping some steps here. Okay, h prime. My current x value is 2, so 1 over 4, or 0.25. And my new y is going to be my current y value plus 0.25 times 1. Oh, and I'm done because I'm just trying to find approximating h of 3, so 1.25. It's possible,
Okay.
yeah.
Okay. It's like here you're trying to like condense it. Is that dividing or is it subtracting? Because I subtracted them, but I don't think since there's a line here.
Oh, this. Or
Next to the one,
this.
just
If you already cancel out,
yeah,
it'll just be.
just x
So how to get from here to here?
subtracting. Subtracting that exponents or the yeah.
Yeah.
You need them a 9 for like the, or 8, because they have like filled ball with those equations.
Mhm. So number 8, we have population growth modeled by logistic equation. What is the greatest rate of change for this population? Um, no, 400. Okay, so the way I worked it out is it says the greatest rate of change. So we know that rate of change is already at the p prime level. So greatest rate of change will be where the second derivative is equal to 0. It's basically like finding your point of inflection. So I'm just cleaning up my p prime to just be with something that will be easier for me to do power rule with. And then once I have p prime, I'm just creating my p double prime, treating p like my variable there, and then setting it equal to 0 and solving for p. Yes. Let's see. What did you get for your limiting value? We
Take 100 and divide by 2 to get p equals 50 and then insert.
right. Yeah. Sorry. Yeah. That's once we can get that that L divided by 2, which is 50. Yeah, that's faster there. And then plug that 50 back in.
Wait, could you explain that? Like,
So we know that your point of inflection is going to occur whenever it's L divided by 2, whenever it's your limiting value divided by 2. So your L is 100, so 100 divided by 2 is 50. Yeah, that's faster. And then we can plug 50 back into the dPdt since we're asking for the rate of change. Specific dPdt value at p equals 50. So we can just plug in p equals 50 at this moment and then find that rate.
can you explain like the whole equation conceptually, like what K, L, and Y means?
So really the most important thing is understanding that your L is your limiting value. It's kind of like your limit, your kind of your greatest possible population. And then your graph is always looking like this. Okay? And then your L is always going to be where your limit is as we approach infinity. Okay, it's going to be that flattening out. And then the greatest rate of change is going to be at when your limiting value, your max value divided by 2 is when the growth rate is going to be at this peak or maximum growth rate. And then there are 2 versions of the logistic differential equation, and I have that on page 5. Either form is good as long as you can somehow figure out what the L value is. So you're always trying to target the L value.
So you don't really have to, like, would a question ever ask like something where you're solving for the K value? Like, what would that look like? Like, what are you solving for when you solve the K value?
If they ask for the K value, they'll have to somehow give you the dy dt. They'll have to give you the y, and they have to give you the limiting value. If you have all those 3 pieces, you can just plug them into the equation and algebraically move things around and solve for K.
Okay. So the question would say something like solve for K. It would like. what
Yeah,
it says.
you'll have to say, to solve for K.
And then is there anything else we should, like, for example, 8 was saying, look for the greatest rate of change to this population. Is there any other like thing we might have to look for where we would have to manipulate?
I think those are the two biggest things, or three biggest things, solving for finding your L,
Mhm.
finding your L over two, and then finding your K.
Okay.
Those are the only three, yes. If you look at all these options, they're all just
Mhm.
either rearranging, just trying to find the different pieces. So if you look at 10 and 11. Yeah, for 11, we could have sped things up just by taking that L divided by 2 to get that 33.
Did you go through 10?
So limit as t approaches infinity equals 100. This is indication that your limiting value L is 100. The rate of change is 5, so that's your dp over dt. Population size is 20. So looks like all these logistic equations are in this form of ky times 1 over 1 minus y over L. So now we just have to find something that can fit into that form. So we know that our dp over dt is our dy dt, that's 5. We know our y is, or our population is 20. So that 20 will fill in there. And then our L is 100. So the only one that's going to fit into that form is this one here. Oh, sorry. So I replaced my DP. Let me rewrite this in the variable that we're using. So I'm replacing dpdt with 5. And I'm replacing p with 20. And then 20 over 100. So it's a kind of a little bit of a guessing check here to figure out, okay, which one of these is going to make it a true statement. And if it's 5 over 16, that's going to work. That's going to allow the right side to equal the left side. And it's just a kind of trial and error here because we don't know what the K value is, but we do know that with this information, both sides have to equal out.
Okay, so basically you narrow it down to C and D and then see which one makes sense.
Right.
Okay.
What's the K value like signify?
It's just the constant that is relating the two sides. So if I have, let's say, two variables that are directly related, it could be y equals kx. And k is just indicating, what that direct relationship is, just some constant that's relating to x and y.
Okay, and did you do 13?
So 13, we have two graphs, y equals x squared plus 1 and y equals negative x squared plus 5. Write an expression that includes one or more intervals that gives the length of the region R. So we're trying to figure out, what is the length of this region here. If we could take this region and put it on a string and and straighten it out. If we're measuring it, what do we let the length be? And we want to use arc length because arc length allows us to measure the distance of a curved region. So we can find the region length from here to here, and then the length from here to here. And both will be its own arc length formula.
So would you have to put it, or I guess you could set it equal, but, so you'd have to find the bounds of where they come.
Right, because we're asking for, we want to know where one length begins and where it ends. And it begins and ends at those intersecting points in the two graphs. So that's why we're going to come to my bounds being -√2 and +√2. So then we can find the arc length of this because we know as we start at -√2, we end at √2, and we know that this is involving our -x squared plus 5, which the derivative is the -2x, and -2x into 4 here, the same thing as with 2x, because I know I'm going to square it, so it's going to end up being positive. And then this one's derivative is also 2x, so that's why they look exactly the same, because my derivative inside the formula is going to end up looking virtually identical.
Oh, okay.
So it's just a coincidence that these are the same. That's why I'm able to merge it together and say 2 times that, or you just say this plus this.
For 14, can you just explain like the general steps of how you would go through this problem?
Yeah, you know that you're eventually trying to get to L'Hopital's rule, but we know we have a variable raised to a variable, so it's not quite in the form that we would like. So we take the natural log of both sides, get it into, so that we bring that exponent down. We use log differentiation. And then once that exponent comes down, we're trying to get this to look like the numerator over a denominator. Now that e to the negative x is pretty helpful for us. I can just make that e to the x in the denominator without doing a whole bunch of algebraic, difficulty there. So that's nice. Now that I'm in this form, I want to convince myself that if I approach infinity, that I'm getting something that is a good condition for L'Hopital's rule.
Okay, so to start, you don't plug anything in because you can't use that yet.
Right. To start, you're just trying to get a fractional setup so
That
that
you can
I
actually
begin
use.
testing. Is it 0 over 0 or infinity over infinity? I got to get one of those conditions to show up before I can jump into my L'Hopital's rule.
And then if you do that first step, you don't get 0 over 0 or infinity over infinity, are you done there? Like if you get a number over 0 or 0 over
Right.
number.
I think what's happening is if you see a problem like this, you know it's going to head towards L'Hopital's rule.
Okay.
And AP exam, they're not going to give you a dead end because they want to see that you understand the process. So
Okay.
they won't do that.
Yeah.
Yeah.
Okay, so you're just forcing it into like the form of like that.
Numerator and denominator. Yeah. And then testing it out, showing out that if you plug in that you're getting infinity over infinity or 0 over 0. And as long as one of those conditions match, you can find the derivative of both the top and the bottom separately. And then reevaluate, convince yourself that you're getting a real number, and then go back and resolve what you're really trying to find, which is y. And because what we have so far is really just natural log of y, we have to do a final resolution and solve for y. My limit is what y equals to, which is 1.
So if you don't get a real number, you just do it again.
You would do it again.
And that would look like
Sorry,
a number.
if you get another 0 over 0 or infinity over infinity, then you would do the derivative again.
Okay.
But chances are, I mean, it's just going to be, if you just give it once, it should get you down to a real number.
Will your end result always be y or y?
No, it's just all the examples that I found are with 1. So, but that's not always the case, but it just, just worked out the way that.
How do you get from like, wait, you move the x plus 1 down to the,
Yeah, I just simplified this so that I have an easier time evaluating this. So I cleaned this up before I figured out that, before I tried plugging in a large number to convince myself what's happening.
okay. And when an infinity is on like the bottom because like it's getting smaller.
It's getting smaller, I know my fractions headed towards 0.
Okay.
But if it's 0/0, it's not a real number, right?
If it's 0/0, then I can do L'Hopital's rule again.
Okay.
Yeah.
And then we have to know our trig rules, right?
Just the trig rules.
Okay,
Yeah, just the basic 6 integral
okay.
rules, yeah, for trig. Yeah, so again, if you know your original 6 derivative rules, that's all you need because you can go backwards to get to your integral rules, right? Yeah.
And then the negative just switches to the other side.
Right, yeah, it's just the other side, right?
What is it? Calculator or not?
Calculator, you can, but I want to see all your work. Or if I want to see all your work, I'm going to specify in that problem with that. You know, show me all your steps. But yeah, I'll give you a calculator.
For number 1, sorry, on this word, I'm so confused on solving.
Sheet 3?
Yes, so I'm so confused on solving 3 of x times f of x. You plugged in the bounds because they didn't give you an f of x value or because you had a definite integral? So when you're solving the 3x times f of x, did you use bounds because you were given a definite integral or because you weren't given the value of f of x?
So we know that this is still inside this integral from 1 to 6. Because after we go through a tab, we would have the version of the problem without the bounds, but because they tell us bounds, we have to involve the 1 and 6 to evaluate these numbers.
Okay,
Evaluate
so
those expressions.
a problem like this, you would always be, if you don't know what your f of x value is, you probably would have a definite integral to work with.
Exactly.
Okay.
Yeah.
Okay. Thank you.
Yeah, otherwise, if there were no bounds here, then your answer would just be this and whatever this plus C is.
Okay.
You wouldn't end up with a number.
Okay.
Yeah.